And I try to make it simple and direct, but it can be, what do I say here? You can flip it both ways. So Caleb's asking about Amazon rainforest, right? Could we say that that's a tragedy of the commons? Like the rainforest is a common area and it's like an open access resource we're destroying. I said preserving it is a public good. Yes, you can flip it both ways. So how I like to phrase it is saving the Amazon rainforest is a public good. Right, so that's how we talk about it. Right, preserving the Amazon rainforest is a public good because it's not rivalrous. Everyone on Earth receives the benefits, and therefore we can say to avoid the free rider. So we're going to be concerned is we're going to have the free rider problem. Do we have the free rider problem? We absolutely have the free rider problem. We say, hey, Brazil, do something, and Brazil's like, well, we're trying, but it's kind of valuable to have it as a soybean field or raise cattle. And so I put it that way. But you can also, instead of saying saving the rainforest is a public good, destroying the rainforest, flip it, is a tragedy of the commons. Right, so destroying the rainforest is a tragedy of the commons. Because that would make, if you take part of the rainforest and you turn it into a soybean field, that's rivalrous. That means then that is diminishing our enjoyment of having it as a preserved rainforest. So, and that's tragic, right? Because now you're diminishing us enjoying it as a rainforest. Generally, right, you go directly for the positive and just say that it's just because this way emphasizes that everybody on Earth receives benefits, right? And that's the free rider problem. And it emphasizes, this way emphasizes that this is a global public good. And therefore, to solve a global free rider problem, it would be efficient to have some kind of conservation fund that every nation feeds into to help with it as a global problem. But yes, you can't flip it, and it's like saving or destroy. So we talk about this. So that's a nuance to what I want to point out. And Noah is asking about the scope. No, he was asking about the scope of the issue. He said, that silly brownies example I did at the end of that in-class exercise, outside of the house, it's a private good, right? Nobody can come in and steal the brownies. So, but it's an open access resource within the household. So the scope always matters, right? So you gotta, and so, generally, if we're looking at local air quality, that's a local public good. And so you're looking at that from, if there's a thermal inversion that has trapped some air pollution just in a certain area, that's a local public good and a local problem. And if you're on the other side of the globe, that isn't impacting you. So it's always, you got to look at it in terms of the scope. If it's climate change, that's always a global problem, right? That's absolutely, greenhouse gas emission doesn't matter where they come from. So yeah, the scope could be local, could be regional, could be national, could be global. With my brownie example, it was one household, and so that is another nuance to always. How can the tragedy of the commons in protecting resources like fish apply to certain hunting permits or fishing permits? So again, we got to see that. Wildlife and Lake Erie are open access resource. Therefore, we're concerned about tragedy of the commons. Therefore, hunting or fishing permits are the solution that solves the tragedy of the commons. Right? So that's the end point. Is you look out there and you think we have plethora of deer, right? You never shortage of deer, but we still have deer hunting permits. So deer are an open access resource, and so we have hunting permits. And so we would not hunt too many deer, so that there would be less for next year. The Ohio DNR is in charge of that. So that not too much is hunted at once. But again, that's the end point. That's the efficient policy. We can say it's efficient because it solves the tragedy of the commons marketplace. Samantha's asking carbon tax. Oh, so the tax and rebate, a little bit of nuance there. If you get the rebate, does that mean then that you'd be like, well, it doesn't matter because I'm just going to get the money back anyway, so I'm not going to change my behavior. If you did it in Canada where they have a carbon tax and rebate. The key is that the things that cause carbon are still more expensive, right? So like a plane ticket causes a lot of carbon emissions, so that's going to be more expensive. And by the law of demand, then people will fly less than they would otherwise, and then you get less carbon emissions. That's the point. And you're going to get that rebate check back. However, when you get that rebate check back, you're going to primarily spend it on something that it hasn't become more expensive, right? You're not going to turn around and spend it all on plane tickets because plane tickets are more expensive now. The relative prices have changed. Things that cause lots of carbon have gone up. Things that don't cause carbon emissions haven't gone up. So you will get that income back, but you still have that price effect. That's something that causes lots of carbon has become more expensive, and you still have a lot of demand. And maybe really the question about is the rebate check you get back is not correlated with the amount of carbon you use. Meaning, if you drop your carbon emissions to zero, you don't get any more of a rebate check back. If you don't care at all and you don't do anything to change your carbon emissions, it doesn't affect your rebate check. The rebate check back is, all Canadian citizens, the amount collected, just divided out, everybody gets the same lump sum check, the same amount, which means you as just one person can change your carbon emissions up or down a lot, and it's not going to change the rebate check back you get. So therefore, you would then have incentive to not connect the two, right? You just look to see things with carbon are more expensive. I'm going to cut back on that. Oh, hey, look, I got this rebate check to go spend on things, but they're not connected. That's the important point. So that's a little more nuance on there. Mitchell is asking, last thing here. Okay, so Mitchell is saying, okay, so we can do corrective taxes. Why can't we do it? I get this question a lot. I would say it's probably inertia in history. Pagot was the economist that first talked about corrective taxes. They were originally called Pagovian taxes after him in like the year 1900. I think was when he first published that. This focusing. This is very focused. hope it fixes itself. But it really took off in the 1960s, right, when the environmental movement began, and we started realizing, pollution levels were getting high, and that we shouldn't just focus on economic growth. That we also want to make sure we have economic growth and clean air and clean water. But by then, we already had a history of income taxes, sales taxes, property taxes. In a way, it's just from the beginning, no taxes were ever designed to consider the environment, and until the last 60 years, and change is hard. If I could blow it all up, if economists could get together and blow everything up and say, let's start over with how we collect taxes at the local, state, and federal level, it would be quite a bit different than how we do it. You start with corrective taxes. So I say it's just mostly history and inertia, and just to make change hard, and really just kind of understanding it. I mean, a tax and rebate would be makes it most possible, and so many countries have done that. The United States has not done that. Okay, so any questions on finishing up chapter 4, open access resources and public goods? These are excellent questions that kind of extra layer of complexity to really show the nuance to that. But that's an important starting point. All right, so exam 2 is going to be what's the rest of chapter 4? That's open access resources. We're done with that. Versus public goods. Okay, so we added that. Today we're going to do chapter 5, and then we'll skip to chapters 11, 12, and 13. These are all about efficient policy. And then we'll see if I get to the supplemental chapter on population. Then later you'll do a current event review assignment after exam 2. After we get all this done, then you'll pick your own environmental problem and talk about efficient solutions. So starting chapter 5. So with emissions, so your book uses the term emissions because emissions means pollution, right? We're gonna zero in on 2 types of costs. If the emissions occur, we've talked about marginal external cost, but now in chapter 5 we're going to call it marginal damage. This is the same thing, right? We're just changing terminology. So now we're going to say this is the marginal damage directly from the emissions. If we allow the emissions to happen, it causes some damage to us or animals or to society, something we care about. Right? So what if we don't want this damage to come from the emissions? Well, then we got to incur some cost to eliminate the emissions, right? And that's called marginal abatement cost. So abate means eliminate, right? So an abatement cost is a cost you've incurred to eliminate the emissions. So either you let the pollution happen, the emissions happen, and we have damage from it, or you incur costs to make sure the emissions don't happen. You're doing one or the other. You're either having the cost of the damage if you let it happen, or you have a cost to abate it. So this chapter is about looking at these two costs. So basically, chapter 5 is all about marginal damage and marginal abatement cost. Right, so we're going to incur one of these two costs. So they both have the term marginal in it, right? We do marginal analysis all semester, and so right, marginal always means additional. So marginal damage is the additional damage from additional units of emissions. And we're going to use E for emissions. And marginal abatement cost is marginal always means additional. It's the additional cost to abate additional units of emissions. E. Okay? So marginal is always means additional. And so we either got to incur one of these two costs. So we're going to start with marginal damage. And so first I want to emphasize how this connects back to what we did prior. So in chapter 4, we used the terminology of external cost, marginal external cost. And so external was outside of the market. Now, so the difference here is the quantity here is the quantity of the good causing the emissions. Meaning like this is fertilizer causing nutrient runoff, driving a car causing greenhouse gases, local air pollution and smog or congestion and accidents, or this is just burning natural gas or coal that causes air pollution and greenhouse gas emissions. Like we did tons of examples of private goods causing emissions. And we said that emissions, that pollution, is an external cost outside of the market, right? The fertilizer market does not factor in these external costs. So it's the same thing, but what we're doing now is we just directly have here E. We're just directly looking at, E here is the quantity of emissions. So we're just looking directly at the quantity of emissions. So let's say we're looking at sulfur emissions that are primarily coming from coal, but we're just graphing sulfur emissions. So we're separating out the emission from the good that's causing it. And then we can just specifically look at emissions, right, and say we generally want to think going this way. We want emissions to go down, right? How can we get from E1 to E2 and reduce emissions? Well, we could add a scrubber, a very expensive piece of technology, in slang is called a scrubber, that in the smokestack that captures the sulfur, most of it, and keeps it from going into the air. So we would just say we would add a scrubber, and that would reduce emissions. And why do we want to reduce emissions? Well, then we're reducing the marginal damage, right? We're reducing the additional, reducing the damage from that sulfur emissions. But we're looking at emissions directly. It's the same thing over here. Well, here it's coal, and we would be like, well, but here we're basically, this is quantity of coal. And so what we're saying here is, if we reduced quantity of coal, lower quantity of coal. Of course, if you use less coal, right? If you use less coal, you reduced the external cost from coal. Here, we separated out emissions from coal usage. We could be like, you could use the same amount of coal, but just add a scrubber, and you can still reduce emissions, right? So we're just now, we want to specifically look at emissions separate from the thing causing the emissions. So that's how it's different. So this is the quantity of coal, this is quantity of emissions. So this is figure 5.1 in your, I'm going to do the first 5 figures in your textbook. And so where do we start? So let's just say a typical average marginal damage curve. And I mean, generally, the most important, there's several important things here. if you have no emissions, you have no damage, right? So you start here, right? No emissions, no damage. As you get more emissions, you would generally expect that marginal damage, additional damage, gets ever higher. Right? This is what we expect to be a typical marginal damage curve is going to look like. If there was only one coal plant in the whole world and it was kind of out in a rural area, no one was around it, it would have some emissions, but it would kind of dissipate and spread out, and there wouldn't be a lot of damage from it. But if you had a second one, a third one, a fourth one, and a fifth one, and then you put it near people, right, then the damages start climbing. So I think that's common that that the damage is going to start low, but it's going to get ever higher, higher, higher. I mean, there's only, if you overwhelm the environment to dissipate a pollutant, then the concentration start really building up, and it really starts impacting people's health, and obviously also animals' health, and maybe even the ecosystem and the health of the ecosystem. So that's what this is showing here. We expect this to be an increasing line. On average, we would just, a generic marginal damage curve, we would just always start like that. So leading it back to what we always said is, if we think something, if we have an emissions problem, if we say it's a problem, well, the market failure here is generally we're going to view us as we are going to start over here. Right? If this is some emissions from some economic activity, if there is no government laws in place to focus on it, then it's going to be ignored in our market economy. That's the market failure. And so we are going to have be nearing whatever the maximum that is just going to happen with no laws in place. So as a market failure, we're going to say start here. You start at Emax. Right? You start on this side. You don't start at zero. You start over here at Emax. That's the market failure. And then we would need efficient government policy to reduce E. Right? And if we're at Emax, then that's a government failure. We don't have laws that are the market failure starts us here, and so it is efficient to have government policy that moves us this way to get rid of that damage from the emissions. If we're hanging out over here, then that's a government failure. Right? We don't have the laws in place to fix that market failure. Right? So that'd be a government failure. And so start here. But now we want to. But how do we know what you reduce it down to? Like efficient government policy. The whole point of this chapter is we are going to show what level of emissions is the efficient level of emissions, and that's unique to environmental economics. To say we're going to prove again there is an answer that's just right based on efficiency. It's generally going to be reducing emissions a lot, but you would only reduce it to zero. Again, if your abatement costs are zero, but generally it's going to cost something to get down. So we're going to add that in a minute. So if we're at a high level of emissions, now let's connect. This is marginals. We can always get the totals from the marginals. If we're at a high level of emissions, what is the total damage from that high level of emissions? Right? It's just all of this. You just add up the area under the marginal is the total. So we can, our marginal graphs show us the totals at the same time. It's just sum up all the marginals. So if we're at this level of emissions, then what area represents total damage? It's this triangle right here. And I labeled the endpoints A, B, C. Right? Sometimes, I can label areas two ways. I can label it as endpoints A, B, C, or usually I do it the easier way. I would just put like a letter A there, right? And then A represents this area or endpoint. So here I'm doing endpoints. So the total damage here is area A, B, C. If we're at that level of emissions, the total damage is A, B, C. If we're at this lower level of emissions, well, now the total damage is, instead of being here, it's here. Right? So obviously, as you reduce emissions, the marginal damage goes down and the total damage goes down. I can move that triangle. If we're doing nothing and we're at Emax, well, then the marginal is here and the total is all this area. Right? So as you reduce emissions, you're reducing the area under the marginal, so you're reducing the total damage to society from that emissions. So first thing there is to know we can always get totals from marginals. Next thing is your book talks about examples of what different marginal damage curves might look like. So if you have a toxic substance, right, what would that mean if it's toxic? That would mean it's very harmful, and maybe even any little bit of it is toxic and harmful, right? So that would be, instead of taking this average marginal damage curve, right, let's just say this is from sulfur emissions, we expect that. If we say these emissions are toxic and really harmful, I mean, generally we're going to shift this marginal demand curve up, right? It's going to shift up, showing that the damages are higher for any level of emissions. And maybe we would be at zero, but even if you take just a discrete jump, a little bit of emissions, it doesn't go here. You just immediately start here, and it goes up steeper, right? So this would be, right, so that might be a marginal damage curve for a toxic substance. Right? I mean, if you have zero of it, the damages are still zero. But E1, even a very low level of these toxic emissions, immediately has a high damage, and then of course it's still going to increase and get worse and worse and worse from that. So this is a generic marginal damage curve that I'm just going to draw like that. If I'm just saying consider the marginal damage from emissions, but where that line is would change based on the emissions you're looking at. Right? If it was something toxic, right, it would start higher and maybe climb steeper. The opposite of that would be sometimes an environmental scientist can study something and say that there is a threshold effect. What does that mean? So right, what's the opposite of this? Would be that. Right? A threshold effect would be a certain amount of emissions is okay, like we don't observe any damages from it. Right? It does dissipate quickly and becomes and quickly transforms into kind of a non-harmful form, and we don't observe any damages to people or animals or the health of the ecosystem. And it's just once this pollution and emissions gets past a certain threshold, we start observing this marginal damage curve. And it could be anything. It could stay flat for a while and then take off, or it could just take off right away. Like every emissions is different, and we can map it out. This is what economists do: is study emissions, and environmental scientists. Scientists are going to study emissions. Economists are going to hang dollars on it and call it the marginal damage curve. Right? So this one, so you can see this is the opposite of that. That's a toxic thing that immediately starts. The toxic one is here and goes high. Something with a threshold, there's nothing, and then maybe it climbs slowly and then it takes off, or maybe it just stays low. It depends. You have to just map it out. Every emission is different. So this would be like some emissions that have a threshold effect and maybe a low level of marginal damage for a while versus a toxic substance. What's the average of that? This. Right? So if I don't specifically talk about an emission, we're just going to draw that. But I do want to emphasize every emission you're looking at. If it's toxic, it's going to be up here. If it has threshold effects, maybe it stays down here. So you would want to be specific about the graph. So figure 5.2, that was figure 5.1. Now figure 5.2 in your textbook, we're still looking at the marginal damage curve. We want to make sure we connect marginals and totals again. And this is emphasizing, again, a lot of this marginal damage is going to affect people. This is an anthropocentric, like human-centered course. And so almost all of the health impacts from air pollution are on people. So if you have more people, you have more marginal damage from any emissions, right? So if you have car emissions in a rural area, right, the marginal damage is going to be lower. If you have car emissions in a very dense urban area, every unit of emissions out of the tailpipe there, the marginal damage is going to be higher because it's additional damages in the nearby area. Well, there's more people, so you have more people impacted, and you're just adding all that up. So again, you start here. So if this is sulfur emissions, let's say this is from a coal plant. If a coal plant is in a rural area versus right near an urban area, same thing, right? You're going to have more people impacted by those sulfur emissions than in a rural area. And so again, you start here. You're going to hear as a market failure if there's no government policy. And we do have the Clean Air Act, which coal plants have to. They don't get to choose. They have to include these $1 million scrubbers to reduce air pollution. And so right, we are down here at a lower emission level due to the Clean Air Act and efficient government policies that lower that emissions. So let's just make sure. Let's first do a class exercise here and make sure as a review of what we just talked about so far. Okay, so I need that. Starting point. Okay, so again, to get the total damages, you just sum up the marginal damage, right? Which means simply it's just the area under the marginal damage curve. Okay, so this is your first class exercise. The question is, so you have 4 letters there, A, B, C, and D. So we're at E1, so this is the point, we're at E1, and we're looking at marginal damage 1 curve. So what letter or letters we're at E1 and we're using this curve represents total damages avoided. And then what letter or letters represents total damages remaining, right? It's different. And then second, just do the same thing but use the other curve. So for 2, let's look at total damages avoided at E1, and now we're using the marginal damage 2 curve. Just put the right letters in there, and then total damage remaining if at E1, and do the marginal damage 2 curve. Equal. All right. So there's 4 letters, 4 boxes. Just get the just get the right letters in the right box. A, B, C, D. Put the right letters in those right 4 boxes. We'll the answers. So what letters goes here? So MD1 curve, he says, in more rural areas. So let's say it's a coal plant in Wyoming, the least populous state 500, 700,000 people in the whole state, less than Columbus, a little more than Toledo, in the whole state. So what letters would go here? What is the total damages avoided that we went from Emax down to E1? What letters we put A, B, C, and D? Is it B? Yes, correct. B is the letter, right? And so again, avoiding the damage is a benefit, right? So this is the benefit of lowering emissions, right? So we're just identifying, and so we would want to claim B as a benefit, right? It's total, avoiding a damage is the total benefit, and it's a total, right? Because it's the total damage emission, right? It's the total benefit of lowering emissions, and we specifically are going from Emax to E1, right? So that's that. So what is the total benefit of lowering emissions from Emax to E1 in Ohio, which has, I don't know how many people in Ohio, but it's the 7th most populous state, many millions. 30 million? Maybe 30 million? So what letter or letters is the total damages remaining? Oh, that's this question. Okay. No, I did remaining first. Okay, what letter or letters represents total damages remaining in Wyoming? That's that next. Okay, what letter represents total damages remaining in Wyoming? Right, D. So that's still a cost, right? That's a damage. That's still the only way you're going to get in this rural area, again, no emissions, is you have to have you have to drive sulfur emissions to zero. And so we're not at zero at E1, so you still have D left, right? So it was B and D, but emissions were lowered. So B is the total damages avoided, but you still have area D, total damages remaining. So so now we just do the same thing. That's Wyoming. Now it's, oops, I put this in the wrong spot. That's what I did wrong. Okay, now let's say this is Ohio. So Ohio means now we're using the more urban state marginal damage curve. So what is the total damages avoided if we're using the MD2 curve? We're still going from Emax to E1. What is the letters now we want? Letter or letters? A and B. Right. Yep. So you got to go A and B. A plus B is the total benefit. Reducing E, and specifically we have exactly going here. I'm saying from Emax to E1. Okay. So how can we look at the Clean Air Act and say it's efficient? Well, we can say, well, or like or specifically requiring scrubbers in coal plants. Well, how much emissions did this technology avoid? Added up. This is in dollars, right? This is dollars. Dollars of total damages avoided is the benefit from the technology. But if there's still some emissions left, you have not driven total damages to zero, right? So now instead of D, right, it's D and C, right? So D plus C is there's still some total damages remaining. There's always total damage remaining unless the only way you get this to zero is you have to drive emissions to zero. Emissions aren't zero. We have reduced it, so we've got some benefit, but there's still some total damage remaining. So again, let's just make sure we understand how we get from marginals to totals and with two different lines here. So obviously, and you can see here, if a marginal demand curve right, has more is higher up, right, you're gonna get more total damage. You're gonna get more benefits from reducing emissions, right, if this marginal demand curve is higher, which is obviously what we're showing here. So in urban areas higher. All right, good. So understood that. All right, so figure 5.3. That's the same thing. Oh no, now we're adding the we're doing the marginal abatement cost curve now. All right, so figure 5.3. So we were done talking about marginal damage. Now in figure 5.3, we're looking at the marginal abatement cost curve. And so we have another line to add. And the key here is, again, you want to read it from right to left. You want to start here. So we have emissions. Let's continue with our story of sulfur and in terms of dollars. And let's just always say we're going to start at Emax. If we didn't have a Clean Air Act saying you had to include scrubbers on coal plants wouldn't have them, and so we would have a much more maximum of sulfur emissions when we're not doing anything. So we start here. So now we say we want to reduce sulfur emissions. Right? So we're moving. So you want to read it. You want to start at Emax, and then you want to read it from right to left. Right? As we're reducing emissions, right? We're going this way. And so you want to think about, then I have the line going this way. You want to think about a marginal abatement cost curve as starting here. It's going to be cheap, and it's going to get ever more expensive to keep driving emissions down. As we keep trying to lower emissions, it's going to get ever more expensive. And so it's that last emission unit to get rid of is going to be the most expensive, right? To drive emissions all the way to zero, it's going to be way more expensive. At first, and the reason here is because at first you're going to do the cheapest things you can. One thing you can do is coal has different amounts of sulfur in it. So the cheapest thing to do is just use low sulfur coal. Then you've lowered sulfur emissions just because you're burning coal that has less sulfur in it. When the Clean Air Act first was implemented and put restrictions on coal plants, this is the first thing they did, was suddenly low sulfur coal was in much more demand as to be used as energy source. And you may ask yourself, why weren't they just using it before? It's a little more expensive, right? It's a little more expensive to mine and go find this low sulfur coal, and they only started looking for it when they had to, right? And then so they started using that. So that's a really cheap way, right? It's just a little more expensive than regular coal. So that's an abatement cost, right? That's a little extra cost to get emissions down. Okay, but once you're using low sulfur coal, now the only way you're going to get sulfur emissions down even more is you're going to have to start putting in expensive technology like a scrubber, right? And so that's a higher marginal abatement cost. It's going to get more expensive with the scrubber, and it's not like all scrubbers are the same and they're just generic. You could put in fancier ones that are more expensive that do a better job capturing the sulfur, and so maybe then you have to even go to a higher technology, more expensive one to get the emissions down even lower. And so that's the idea, right? Is that generally, on average, again generically, to lower emissions, you start off doing the cheapest things first, But then once you've done the cheapest thing, you got to do something more expensive, and you got to do something more expensive, and you got to do something more expensive to keep lowering emissions. So we always draw a marginal abatement cost curve going this way. You want to think of it reading it right to left. So as you reduce emissions, this leads to the marginal abatement cost curve increases. Right? You're going to see that the marginal abatement cost curve gets very high as the emission gets close to zero. So now we have both of our graphs. Now, why we do both these graphs? Well, you can see the dollars in emissions is the same. So now we just got to bring them both on the same graph. That's the whole point of this chapter. So figure 5.6 in your textbook, right? Let's show both the marginal abatement cost curve and marginal damage curve on the same graph. Right? And as I said previously, we're trying to do simple graphs to show us efficient solutions. And it's always where the two lines intersect. That's always what marginal analysis is. So it should not be a surprise that I can say, now that I have this information, what is the level of emissions that is efficient? Where do these two lines intersect? That's E star. So wherever these two lines intersect. So E star is the efficient quantity of emissions, and we're using the equimarginal principle to get us there. Let's do that next. So we just did an in-class exercise that we can get total damage from the area under the marginal damage. You just did that. So I'm going to assume then that you can also understand that we can get total abatement cost from the area under the marginal abatement cost, right? And so if we have a lower marginal abatement cost, then you're going to have, if you have a marginal abatement cost at some emission level less than before, your total abatement cost is also going to go down. So total abatement cost is you sum up the area under the marginal abatement cost. Same thing. So we're going to use that. Because what we're going to do next is prove, how are we going to prove where these two lines intersect is the efficient quantity. So let's switch, and I'm going to do the example of fracking, hydraulic fracking that allows us to get natural gas and oil. That next. So let's see, put some thoughts to this article. So we're going to switch to fracking. So right. So are we going to look at, let's say some environmentalists would like to completely shut down hydrofracturing, which we'll just call fracking. This article is summarizing a report that says shale gas can be safely extracted in a relatively low-cost way. And again, certainly using natural gas is preferable to coal in terms of, again, sulfur emissions, greenhouse gas emissions, really any air pollution you want to measure. Natural gas is much cleaner than coal. Of course, it's solar and wind, geothermal are cleanest because there's no air pollution from that, but it's cleaner than coal. But the report also makes clear that regulators in the industry would be efficient to be much more aggressive in protecting water and air pollutants released from the process of fracking. You got to have leak-proof wells. You have to safely recycle and store millions of gallons of water if it becomes contaminated from the process. And now, if you're an oil or gas company, this was one of the questions on the exam. It was surprising to me how many students missed this. If you are an oil or gas company and we're talking about regulations that are going to limit pollution from fracking, what do you think you're going to emphasize? Right? You're going to emphasize this costs extra. This is going to be terrible for our business. And there's some gas plant locally, and we're gonna not be able to compete. Maybe we got to lay some people off, job losses. Like they're going to make it sound as horrible as possible. They're going to emphasize the cost. And we're talking about this chapter, they're going to emphasize the abatement costs, right? Because that's the cost they have to bear, right? That's the cost to them. And so they're going to emphasize that, and you're going to not be happy about it. And generally, you don't see a company putting out a news brief saying, yes, please regulate us and make our costs higher. No firm does that. Right, so you're going to have, like here they're saying warfare against, they're saying necessary regulations, this report says, based on efficiency. So they're going to make it sound very burdensome. So this article says, would protecting the water and air bankrupt the industry, right? Meaning these regulations are so expensive that they would just stop fracking in places. No, the report estimates that operating with a near zero impact, not zero, but near zero, like you can dramatically reducing the air and water pollution, the marginal damage impacts from fracking in an area, it would add about 7%. It would be a 7% cost increase. So $600,000, right? That's a lot. But a typical well has an $8 million cost. So you're changing it from $8 million to $8.6 million, a 7% increase, right? If you're running that well, you're gonna complain about this number and inflate it and make it sound massive and burdensome and just forget it. You got to shut it down if you do this, because the whole point is to try to prevent this policy from becoming in place. And so again, this emphasizes what I showed you right before break. Is what are the trade-offs? We can reduce pollution, but it's not zero. But relative to the cost of just running our economy anyway, it's a 7% extra cost to get a near zero impact. It's not 70%. It's not 170%. It's not 700%. If it's 700%, forget it. You're not fracking anymore. It's 7%. But they are going to act as if it's 700%, and it just destroys the industry, right? So, but we haven't done it, right? We have some laws, but we still have fracking causing as an environmental problem because we haven't put the efficient regulations in place. So companies have to incur this extra 7%. There are laws in place, but they are not stringent enough, right? The necessary regulations stringent enough to get a near zero impact. So let's graph that. Take that article and okay. I call it the Goldilocks story. So let's take that article and use it as an example to apply what we learned in this chapter. So let's say you're a green bear, you're an environmentalist, and you're growling because your goal is to end fracking, because you want emissions to be zero and you want total damages from fracking to be zero. And the way to get total damages from fracking to be zero is to have marginal damages to zero, so it has zero emissions, right? You want to be here. That's your goal as a green bear. All right, well, you're ExxonMobil, and so we'll say black bear is the business, and you're growling because your goal is to eliminate any regulations because you want to make abatement cost zero, because your job is to maximize profits to your shareholders, and you'll lose your job if you're not doing a good job of that as the CEO, and they'll replace you with somebody who does a better job of making sure share prices go up. Right? That's entirely your job. If you're in the business of running ExxonMobil, your whole entire objective is to maximize profits. So the only way, if you can get abatement cost to be zero, then you get maximum profits. That's the right here. That's no regulations. Okay, well, which is it? Do we want no damages, or do we want no abatement costs? So that's the extreme, right? You either have no emissions, therefore no damages, or you have no regulations whatsoever, and you have maximum emissions, but you have no abatement costs. And so if this is the story you want to tell, you're going to make it sound like this abatement cost, right, is like, if you try to do anything at all, like it's just this massive abatement cost that's just so burdensome. It would really be awful to do it. If you're going to be an environmentalist and you want to just try to make it, you want to try to drive E to zero, right? You want to make it sound as if like it's like any emissions coming from fracking is like that damage curve from toxics. It's just massively toxic, and the damages are so high, you should be there. Normatively, right? Normatively, you want to be here. Normatively, they want to be here. All right, so this is the story I come up with. Well, who's right? So let's be a scientist and say neither of them are right. The efficient E is wherever those two curves intersect, right? So Goldie is the environmental economist who's growling because neither of them are using the eco-marginal principle and doing marginal analysis. And so to find E star, our goal to bringing these two damages together is we want the quantity of emissions that minimizes total social cost. So your book calls it total. So what is total social cost? You just add up the total damages from the marginal damage curve, and you add up the total abatement costs from the marginal abatement cost curve, add it together, that's your total social cost. So the eco-marginal principle says to achieve efficiency, equate our generic eco-marginal principle is to achieve efficiency, equate the relevant marginals. That's always, right? This is always. And now we want to apply it to this specific example in chapter 5. And so here, our efficiency goal is to minimize the total social cost from emissions, which means we are equally caring about damages from emissions and we are equally caring about abatement costs from emissions. We're just adding them together. Like we want to minimize this, which includes both pieces. So how are we going to make sure we've minimized the total cost of society from emissions? Well, just find the emission level where these two marginals are equal, and we know then that the total social cost is minimized. So that's how we're using the eco-marginal principle. That's saying in words. So where these two, so you want to think of this, you want to think of it starting as right from left, like how we usually do the eco-marginal principle. So we want to say, is it efficient to lower emissions a little bit? Yes, because the marginal damage avoided, that's the benefit. The benefit is greater than the cost we've incurred. A little more, yes. A little more, yes. A little more, yes. A little more. Stop. Right where these two lines cross. Right, so you want to think of it again. You got to read this from right to left using the eco-marginal principle. Right? Because we are going to start. The market of failures is we are going to start with emissions that's too high, and then you must have government policy. So again, you have to start at Emax and read from right to left. Okay. Reducing E. When you reduce the marginal damage, that's the benefit. But you're increasing the marginal abatement cost. That's the cost. Right? So we got to compare the benefit and the cost. And so keep going, stop. We can't be the green bear based on efficiency and drive that emission to zero because it gets too expensive, right? If you blow right past E star and you drive it all the way over here, you have minimized, you have no damage, but society is incurring some really massive abatement costs that aren't worth it based on the little bit of damages avoided. So keep going, stop. That's the eco-marginal principle. So today we did the marginal damage curve, we did the marginal abatement cost curve, we graphed them both, and we said right where they intersect using the eco-marginal principle is E star. So I covered, there's 6 graphs, this is figure 5, 6 in your textbook that brings all that story together. So questions you have so far? It's going to take a little bit, make sure you can work with this graph. Again, the key is you read it from right to left. We start here, and we're thinking about marginally. What if we have policy that gets us to here? Well, that's better, but we're not at E star. What if we get to here? Perfect. What if we have policies too stringent? What does that mean? Well, you blew past E star, and you would actually have laws that are too strict in terms of lowering emissions. Now, the number of stories I can tell, almost, why do we still think we say things are environmental problems? Where are we at on this graph if we credibly are talking about articles of having environmental problems? Where are we at on this graph? Compared to E star. Okay, we're over here, right? We've done something, but we're not there yet. So it's still an environmental problem. I would love, 20, 30 years in the future, I don't think we'll ever actually get there. So I could say, we are at E star, and some people may say still it's an environmental problem because your goal is to drive marginal damage to zero. And I can say, well, it's too expensive. Then the goal is we have to, let's just add another thing. Let's do. I was going to say next. If we had a technological advance in pollution reduction, how would you show that in this graph? So let's just make sure you understand that. Okay, so our second class exercise for today. Let's say we have a technological advance to reduce emissions. Let's say that we use. Right, how would you show it in figure 5, 6? All right. So take this figure 5, 6. How would you show it, and then how does E star change? Okay, do that and we'll talk about it. Make sure that you understand how to use this graph. So our marginal abatement cost curve, our marginal damage curve. There's a technological advance, meaning that we can reduce it. What does that mean? I mean, if it's a technological advance that we're going to use, it means we can reduce emissions in a cheaper way. So how would you show that in the graph? And then how would that impact E star? Do that and we'll go to the answers. How would you show it? How does it change E star? There's two questions here. All right, so how would you change figure 5.6 to show a technological advance that we would use to reduce emissions?
The marginal abatement curve would shift to the left.
Right, left or down. Right, you want down in dollars, which is also left. Yep, so it would be down and to the left. And so if you shift it down and to the left, then what happens to E star?
It becomes smaller.
Becomes smaller, right? So that's what we want. We want technological advances that allow us to reduce emissions, because then we would say, oh, we can get rid of emissions more cheaply, keep marching down this marginal demand curve even more now. Right, so I want to draw. Yeah, I'll show it here. Right, so it generally look like this. Either is down or to the left. And then the whole point is then, well, now this is E star. E star is just call it mu. Right? So the marginal abatement cost curve shifts down or left. That's equivalent. How does E star change? It decreases. And so what I was going to say next is, as a society, if we want efficient policy to be always decreasing emissions, then we got to get technological advances so that we can reduce emissions more cheaply, and then the efficient quantity of emissions reduction does decrease. And then we would say, so as we can get closer to zero emissions if it becomes cheaper and cheaper to have that. I don't have to do the next story. Okay, so just saying in words, we're going to prove it next time, but I don't want to do it today, so we'll do it on Monday. So you want to keep reducing emissions, right? Again, like I said, starting from right to left, so long as the marginal abatement cost is less than the marginal damage. You can keep going until they're equal. Stop. That's the eco-marginal principle. Just when these two are equal, because then we reduce all emissions where the abatement cost was less than the damage that it caused. And in that way, we minimize total social cost of society. And so when we do in a society, we care about both abatement cost and damage. So if abatement cost is cheaper than damage, do it. So keep going, keep going, keep going. Stop. You must stop there, because if you go past that, well, you are still, of course, always reducing damage, but now it's just become too expensive. The extra cost you've incurred to get rid of that emissions is higher than the damages you avoided. And so in terms of total social cost, which is adding up both of these, this number is bigger than this number. So you went too far. So you would go too far if you went here to MAC3 at this point compared to MD3. Right, you went too far, and that's wasteful. In terms of dollars, you spent too much money based on efficiency for abatement cost versus what you gained from it. Right, this is so this is saying the cost, the marginal cost is greater than the marginal benefit. All of economics is a cost-benefit analysis. It's just with emissions reductions, the abatement cost is the cost, and the marginal damage avoided is the benefit. And we've gone too far here. The marginal cost is greater than the marginal benefit. So we'll prove it next time with letters and make sure we understand that. But what I want to say next is, so we talk about technological advances can reduce this here, but also we have research and environmental scientists and health scientists and economists work together. We are still always learning about marginal damages, right? And what we know about that. So 2 minutes left here. I'll just skip to this one article. So this article left. So this is the Journal of the Association of Environmental Resource Economists. This is the #1 journal in environmental economics in the world. If you publish here, journals kind of generally have rankings of like, if you get published here, it's like they have about a 10% acceptance rate, 90% of papers. It's like getting into Harvard as a student, right? Like getting a paper in this journal is the hardest. Just came out this year. So they looked at 1.8 million university course grades for 89,000 students. And what they found is they looked at local air pollution combined to how students did on exams. So they find robust evidence of a negative and causal effect of exam day outdoor air pollution on course performance. Women were more sensitive than men, and if you were doing an unfamiliar task, which means you got to use more brain power, that air pollution affected you more. The level of detail here is amazing. If you're in a newer building, especially if it's a high quality environment that has the LED gold like standard of how it was built, it provides significant mitigation of outdoor air pollution. They even looked at floor level. If you went up a floor, the ground level air pollution is higher and you went up a level. And the amazing thing here is, I saw this and I'm like, okay, sure. I mean, lots of these articles have been done in high pollution areas in developing countries, maybe in a crowded city in India, which is generally higher air pollution than in wealthier countries like Canada, the United States. But this was Canada. They found this. So exposure to polluted air is well understood to damage human health. Right. This is the beginning of the paper. They argue, especially on mental function. So this is a summary of all these other papers. People have looked at it in terms of productivity of work quality, communication, financial decision making, consumer behavior choices, even interpersonal violence. Air pollution causes people to make poor choices on a test, and rash choices in terms of violence. So what is the particular pollution they're looking at? Fine particulate matter, so the smallest, PM 2.5. Right? Historically, we focused on PM 10. PM 2.5 is these really tiny particles that you can't see, but they still get into your body and affect your brain and lungs and cardiovascular health and also brain health. So they were focusing just on that and looking at scores. So they knew the building in which they were taking the test. They knew the room location, and again, they knew the floor you were on and how modern the building was. So it's an incredible level of detail. So they find evidence on the mental productivity based on these exam scores. So how did they test this? Well, again, these are these thermal inversions, a meteorological phenomenon where the layer of warm air traps air pollutants at ground level. And so about 30% of the time, this would happen. So over this time frame, they can check to see when these thermal inversion events are happening, and they can measure it and see the air pollutants are going to be higher at ground level on those days. Did students score worse? And the answer is yes, they did. They scored worse based on the building they're in, based on whether they were on the third floor or the first floor. Right? This is incredible level of detail. And days prior, also days leading up to the exam too. Like it has a temporal impact. Like if that thermal event was 3 days ago, that still is going to carry over onto the exam day. So has been known for decades. But what's new, this was in Ottawa, one of the cleanest places in the world to be taking an exam. Their average annual concentration of this particulate matter at 2.5 was 6. It's 15.6 in Paris, 51 in Beijing, and 113.5 on average in Delhi, India. This isn't Delhi, India. This is Ottawa, Canada. It's 6, not 113.5. But it's still, they could tell that it's detracted from cognitive performance, even in this low pollution setting. Suggests there may not be a threshold below which air pollution no longer matters. So we are learning, right? So this just came out, right? So economists are studying this and constantly finding. So we're looking at, here's the emissions, and it's particulate matter 2.5. The absolute small, you can look out there right now and be like, this is a gorgeous day. There's PM 2.5 out there. How much? We can measure it. Right, so this is dollars, marginal. We maybe thought before, this is the marginal damage. There's some threshold. It's okay. This is the cleanest air in the world, and we can tell it affects your ability to take a test. It's here. So is it efficient to get that number lower now that we know this? Yes, right? So science helps tell us, and it is efficient to lower air pollution. Can we get particulate 2.5 near zero? Yes. Stop burning fossil power, use clean energy, drive electric cars. Right? So we are getting into a world where it is efficient to be there using our marginal damage, marginal cost function. We're just not doing it. And we keep finding the science that says this is higher than we think. And the abatement cost is cheaper than we think. So keep going this way. And our laws just aren't keeping up with us to push us that way. All right, so I'm out of time. So we are daily writing now. And next time I'll finish up this chapter and we'll do the proof and more examples with this new graphs.
you.